Hello, my name is and today I'm going to do my chemistry presentation. My first topic is chemical nomenclature. Chemical nomenclature is a system used to name chemical compounds in a standardized way so that scientists across the world can communicate clearly. It makes sure that each compound has a unique name that reflects its chemical composition and structure. And now we're going to go over the difference between ionic and covalent compounds. An ionic bond is when a metal gives up its valence electrons to a non-metal. This turns a metal into a cation. This gives the metal a positive charge since it has more protons than electrons, and this turns a non-metal to anion since non-metal absorbs valence electrons from metal, turning it to anion since it has more electrons than protons, and giving the non-metal negative charge. Non-metals need to form complete octets. So in order for them to do this, they must combine with one or more metals depending on how many valence electrons the non-metal has. Oxygen will need to bond with 2 sodium ions to form a complete octet due to the fact that oxygen has 6 valence electrons and sodium has 1. A non-metal needs 8 valence electrons to form a complete octet. A covalent bond is when 2 non-metals share valence electrons in order to have stable configuration. An example of this would be oxygen combined with 2 hydrogen atoms to become stable. Or chlorine and fluoride coming together to form chlorine fluoride, which completes the octet for both of them. And I drew out some examples. The first, I did 2 for covalent and then 1 for ionic. So as you can see right here, oxygen has 6 valence electrons, hydrogen has 1. In order for the oxygen and hydrogens to have a complete octet or 8 valence electrons, they must combine together because oxygen has 6, hydrogen 2 hydrogens, and that forms a complete octet. That's 8 valence electrons. Now we're going to go over the chlorine and fluoride. They both have 7 valence electrons, but they need 8 to form a complete octet. So what they do is that they combine together and share that last valence electron right here, as you can see. One of these belongs to chlorine and one of these belongs to fluoride. So they combine together and share that last valence electron to form a complete octet. And then this example of ionic bond. Let me read this. This is magnesium and oxygen, but I know it's hard to read like this, my bad. But right here, you see magnesium has 2 valence electrons, oxygen has 6. In the ionic bond, magnesium is gonna, magnesium is gonna give up its valence electrons to oxygen, so oxygen can form a complete octet and have 8. So this is what happens: magnesium becomes positive, giving up its valence electrons to oxygen, and oxygen forms a complete octet. Okay. Now I'm doing my binary ionic compounds. So for the first one, it's sodium and phosphorus. Because it's ionic compound, we don't have to do mono, di, tri, hexahepta, or any prefixes. We just write it out for what it is. So we see sodium and phosphorus. So it's going to be sodium, phosphide. And then for number 2, we're going to need a periodic table. So for number 2, magnesium can give up 2 valence electrons, and nitrogen has 5 valence electrons and needs 3 more. So basically, we're gonna have to do some math for this one. So if this one needs 3, but this one can only give up 2. That means we have to do 3 times. We have to basically switch them. So basically, you need so if this one only has 2 to give up, you need to have 3 of these ones for magnesium. And then if this one if this one needs 3, then you're going to have 2 of these ones. So magnesium has, so 3 times 2 is going to be 6. 2 times 3 is going to be 6. This one needs 3. This one can only give up 2, and that's how I got my answer for binary ionic compounds. Now we're doing transition metal compounds. So for transition metal compounds, you need to use Roman numerals to describe how many valence electrons each cation is going to have. So the cation in this situation is going to be lead. So Oxygen has 6 valence electrons, meaning it needs 2 valence electrons to form a complete octet. Lead can have anywhere from 2 to 4 valence electrons, depending on how many we would need to have since it's a transition metal. So, because we need the lead to have 2 valence electrons, the name is going to be lead oxide. Okay, so basically we're gonna have a little bit more complicated with the same problem. Manganese, we're gonna have manganese, IV or 4 phosphide. So manganese can give 4 valence electrons. Meanwhile, phosphorus needs 3 valence electrons to form a complete octet. So we're going to have to do crisscross formula in order to find the in order to write the formula. So basically, it's going to be Mn3 because we have 4 manganese, and then because we have 4 valence electrons in the manganese. So we're gonna need 3 manganese and then phosphide. So P4 because phosphorus needs 3 valence electrons. So we're gonna need 4 of these, and then we're gonna need 3 manganese. And yeah, that's how you write out that equation. Now we have polyatomic ions. For the first polyatomic ion, we have magnesium phosphate, and we're going to have to write out the formula for magnesium phosphate. So magnesium can give up 2 valence electrons, and phosphate is going to need 3 valence electrons. On top of that, phosphates, you write phosphate as PO4. So, okay. Magnesium needs 2, so we're gonna have to do the crisscross formula. Or magnesium to give up 2, phosphate needs 3, so we're gonna have to do the crisscross formula. We're gonna need 3 magnesiums and 2 phosphates in order to give phosphate its complete octet. So we're going to need Mg3, since it can only give up 2 valence electrons. And then the formula for phosphate is PO4. So we're gonna have to write PO4. We have to put this in parentheses. And then 2, since it needs 3 valence electrons. And this is the, let me write this more clear. This is the formula for magnesium phosphate. Now we have iron 2 arsenate. So, let's see. So this iron can give 2 valence electrons. Arsenate needs 3 valence electrons. So we're gonna have to write it like this. So Fe, since it can only give up 2 valence electrons, we're gonna need 3 irons. Fe3, and we have to put this in parentheses. The formula for arsenate is AsO4, so AsO4. And then we're going to need 2 arsenates to form a complete octet, since arsenate needs 3 valence electrons. And that's how you do polyatomic ions. Now we're going to talk about moles. A mole is a unit in chemistry that represents 6.022 times 10 to the 23rd power particles. It allows chemists to count very large numbers of particles using measurable amounts like grams. The mass of 1 mole of a substance equals its molar mass in grams. The number of particles in 1 mole equals Avogadro's number, which is 6.022 times 10 to the 23rd power. Some examples of the molar mass of individual elements are: the molar mass of carbon is 12.01 grams per mole, and then the molar mass of carbon dioxide is 44.01 grams per mole. Okay, so we're going to convert 30 grams of carbon to moles. As you see in the periodic table, carbon has a molar mass of 12.011. So this is how we're gonna set this up. 30 grams of carbon over 1 times 1 mole over 12 grams of carbon, because there's 12 grams of carbon in 1 mole of carbon. We're gonna cross multiply this right here. So we're gonna end up with 30 grams of carbon over 12 grams per mole. And that's it. We're gonna end up with, let me use a calculator. 30 divided by 12. 30 divided by 12. We're gonna end up with 2.5 moles. 2.5 moles of carbon in 2.5 moles of carbon in 30 grams of carbon. And that's gonna be our answer. Avogadro's number is 6.022 times 10 to the 23rd power. This represents the number of atoms, molecules, and ions in 1 mole of any substance. 1 mole of any atom is 6.022 times 10 to the 23rd power of atoms. 1 mole of any compound is 6.022 times 10 to the 23rd power of molecules. And these bridge the gap between microscopic quantities and macroscopic quantities. So, how many moles are in? So for Avogadro's number, we're going to do this problem. How many moles are in how many atoms are in 5 moles of oxygen? So we're gonna have to multiply 5 by Avogadro's number. Six point 022 times 10 to the 23rd. Five moles times 6.022 is going to be 30.11. We're gonna have to move this back one, just and then we're gonna have to add an extra exponent to this right here. So it's gonna be 3.011. 3.011 times 10 to the 24th. 10 to the 24th. So it's going to be 3.011 times 10 to the 24th atoms in 5 moles of oxygen. And just for fun, we could do the math on that to find out the actual number of atoms. So we're gonna type in the calculator 3.0. Well, actually, no, we're not even gonna be able to find the actual number. That's gonna be too big of a number. Just need to write it down. So, just for fun, this is how many atoms would be in 5 moles of oxygen. That's a lot of atoms. Avogadro's number is obviously really large, and a real world analogy is if you had 6.022 times 10 to the 23rd power grams of sand, it'd be enough to cover all the beaches on Earth and form a layer of several meters thick around the entire planet. So that's a lot of sand, and yeah, this number is really huge. So that just shows you how small atoms are in comparison to everything else. So just think about how many atoms are in a human being, or how many atoms are like in something simple like a laptop or a phone, or even something like my periodic table right here. So that's kind of interesting to me, honestly. Molar mass is the mass of one mole of a substance, and it's measured in grams per mole. It's found by adding up the atomic masses of all the atoms in a compound using the periodic table. So, like, the molar mass of carbon would be 12.011. Molar mass of oxygen would be 16. Molar mass of fluorine would be 19. Molar mass of neon would be 20.2. Molar mass of barium would be 137.33. So yeah, that's what molar mass is. Okay, so for the example of molar mass, we're going to find the molar mass of sodium bicarbonate. So first we have one sodium. One hydrogen, one carbon, and then 3 oxygens. So we need to find the molar mass of sodium, which if we go up here to the table, we find Na. Molar mass of sodium is 22.990. So I'll probably just round it up to 23, honestly. So Na is 23. Okay. Now we need to find the molar mass of hydrogen. That's up here. Molar mass of hydrogen is basically 1. It's just 1. We have to find the molar mass of carbon. Right here, molar mass of carbon is 12.011. Let's see. And then we have 3 oxygens in sodium bicarbonate. So molar mass of oxygen is 16. We have 3 oxygens. 3 times 16. We can do that in the calculator. I don't have my actual calculator with me because I let my friend borrow it for a chemistry exam. So I just have to use my laptop. The 3 times 16 is going to be 48. Is 48. So we have to add everything up. 23 plus 1 plus 12.011. Plus 48, and that is equal to a molar mass of 84.011 grams per mole for sodium bicarbonate. For fun, we're going to try to find 100. Matter of fact, we can do 1,000 moles of sodium bicarbonate. So 1,000 moles of sodium bicarbonate in grams. So we see that it's 84.011 grams per mole. That's how many grams are in 1 mole of sodium bicarbonate. So we have to multiply 1,000 moles by the molar mass of sodium bicarbonate, which is 84.011. 84.011. We do this right here. You type this in the calculator. Times 1,000. So right here. That's the 84,011 moles. 84,011 grams and 1,000 moles of sodium bicarbonate. This ends my presentation. I would like to thank you for your time. Thank you for listening to what I had to say. And Yeah, thank you for teaching us. Thank you for teaching our class, and thank you for, I'm trying to say, just trying to make the most out of everything going on right now. I really appreciate everything you've done for us, and I'd like to thank you. And thank you for listening to my presentation.